right, absent people, we are going to hop on page 22 of the notes. It should look like, let me clear it off. And we're just going to do a little recap below example 3 here. I'm going to make the screen bigger for you while everybody's opening theirs up. All right.
I would have water, I could have done it.
You're not supposed to have water, that's why it's impossible.
It's like that epic fail thing. All right, so this is what I want you to do on this page. Go ahead and, we're actually not going to do example 3 right now. I'm sorry, someone's sharpening their pencil. I want you to draw a little line right here, and we're going to kind of just do a little timeline of what you've been doing, and then it'll move into the next part of the chapter. All right? So when we started this chapter, go ahead and draw this, because it's good for you to see the flow. We're a little over halfway through. We had some function, and when we first started, it was called f of x. And it was y equals f of x. And our goal was to determine on a closed interval, okay, what the area is between the curve and the x-axis. And we didn't know how, and historically they didn't know how. We only could approximate it. And that's what those of you, 3 of you, making up that quiz today, that's what it's kind of about. All right? And we did it 4 ways, actually. We said, well, you can do rectangles that hit on the right, or you could do rectangles that hit on the left, or you could do rectangles that hit in the middle. I'm just doing kind of, it doesn't really matter. We chopped it into rectangles, and these were approximations for what we called a definite integral, and they were approximations for the area there. They were not exact, they were off, right? And then they turned into word problems where this became time, like maybe in hours, and then maybe it's just like, maybe it's something being manufactured in parts per hour. So that when we actually did our area, our bases times our heights, the time would cancel, and the area would represent how many parts were made, right? And then we also did it with trapezoids, but they were all estimates. Remember doing that? All right? They were not exact because even historically, that was a big issue, is how do I get underneath that curve? To do it exactly, we moved on and we said, well, you know what? I could do it exactly if it was all geometric. So if I had a triangle, a semicircle, and a square, then I actually could get it exact by just doing geometry. I could just do half of the base times the height, 1/2 pi r squared, side times side, and I would get it to actually be equal to something exactly. But we couldn't deal with curvature unless it was part of a circle, because that's the one we have formulas for. But we did that for a while, right? And it'd say to integrate from here to here, you do the triangle plus the circle minus the square, right? And then after that, it became a word problem again. And maybe this was time in hours. And we talked about snowfall quite a bit, so I'll do in inches per hour. Then when we integrated, that area became inches per hour times hours. It became inches of accumulated snow. We called it accumulation, right? So we would have said it's snowing faster and faster and faster and faster, still snowing, just slower, faster and faster, still snowing, accumulating inches and inches of snow. And then what happens here in that analogy? It starts to melt, and when I'm done, I have an amount of snow. Are we good with that? That's where that went. And we're going to go right here. Then we said, well, you can use your calculator to do it exactly, right? So let's split this, and that's where our rate in, rate out came in, where we would say, all right, there's some function that maybe is telling me how much is going in at a certain rate and out at a certain rate, and there's amount present at a given time, and I can use my calculator to integrate those rates. Just use Math 9, right? So we did it actually 3 ways is what we've started with our integration. We approximated with rectangles, left, right, middle, and trapezoids. Then we said, let's go exact. Well, we can't, unless we keep it with geometry, or we have a calculator. All right, so that's kind of where we've been. Now in the bottom box, we're going to go back to the curvature. Okay, so we're going to go back to having functions that have curvature to them. We are still going to be looking on a closed interval, but we are going to have a method by hand, analytically it's called, like by cranking out some work for getting the exact amount. All right, so that's our end game is, all right, we don't want to approximate. In the real world, we don't get rectangles and squares and triangles. Math 9's nice, right? If you know the function. We like that. Actually, a Math 9 and the by hand are the two good ones because they're both exact. Are you ready? Okay, so our goal today, I'm going to move on to the next page, is going to be a process that'll reach that end game. You won't be doing that yet today, but we're going to do something. It's a process called anti-differentiation. So you're going to be kind of working backwards. So right here it says, suppose we want to find a function whose derivative is 3x squared. Go ahead and write one down. A function where if I said take its derivative, you go, oh, it's 3x squared. Because we know how to do derivatives. Well, actually, you wrote one down right away, right? What polynomial or function would have a derivative of 3x squared? Go ahead, Kristen. X to the third. What's its derivative? 3x squared. But there's another one. There's actually an infinite amount more. Want to give me another one? Yeah, go ahead, Jacob. Ah, I love it. X to the third minus. I don't even care that I didn't hear him. Right? Because what's the derivative of any constant? It could be x cubed plus 5. The derivative of all of those is 3x squared. Do you agree with me? And so in particular, we call it x cubed plus c. And c stands for any constant. It's morphed over the years of me teaching it as being Carl. Okay, so we're going to be talking a lot about Carl. He's on the shirt back there under the ambulance that stood for, they used to always say, well, hospitals. And they said, let's put help Carl under it. He actually had a kid named Carl back here. So anyway, this became Carl the constant. You're going to hear me saying, you forgot Carl. Don't forget Carl. Even last hour they were doing the delta math. They're like, do I need to spell Carl with a small c or a big c? It doesn't matter. But so we're already calling it Carl last hour. But all of these guys up here and these all have a derivative that's 3x squared. If we were to write this as a mathematical statement, we would say I'm going to give you some language. Are you ready? There's a lot of language today. So there's a couple ways I could read that. When you integrate 3x squared with respect to x, you get x cubed plus any constant. Or we could say the antiderivative of 3x squared is x cubed. Or we could say anti-differentiate 3x. It's it's like going backwards. So the derivative of this is always the integral. Okay? Our goal is going to be to figure out what this is. You could just see it for that one, correct? And there's some there you're like, I can just see it. If I said, what's the antiderivative of cosine x? In your brain, you have to think the derivative of what is cosine? Sine. Sine would be considered the antiderivative of cosine. All right? Its derivative is. See what I mean? There's a couple you're going to intuitively know. What do you think the antiderivative of e to the x is going to be? E to the x, because its derivative is e to the x. There's others that get very complicated and difficult, but that's not today's task. All right, so we need a few rules. The first one is that the antiderivative of 0 is any constant in the world. Because if I said to Mandy, what's the derivative of 5? She'd say 0. But I said, what's the derivative of 7? What would you say? 0. Okay? So this guy's derivative is this. So if I were to say we've got this other constant, like the antiderivative of 5 dx, I'm saying the derivative of what is 5. And what would you tell me? Well, 5x, right? Plus 8 or 9 or 10 or 11 or minus 44. Correct? So this would be a plus C. It's kind of like going like this. The square root of 9 is equal to 3. Why? Because 3 squared is 9. You might call it the anti-square root instead of the antiderivative. All right, we're nodding. So next up, constants can, and often it will make your life way easier, come out front. So all that's saying is if, and we talked about that one yesterday, if you have a 4x squared dx, you can just ignore the 4, pull it out front, and then do what's called anti-differentiating. Also from yesterday, we can split up sums, and we can split up differences. Did I say products or quotients? Those can get really complicated. Like trying to figure out the antiderivative of this is incredibly difficult. There is one, but you won't learn that for a while. Okay, today we're going to stick with kind of the equivalent if I said, hey Bella, what's the derivative of 4x cubed? She'd go 12x squared, right? Power rule. We're going to have what's called the power rule for integration. And then we're just going to practice it, and you're going to go to work, and it goes pretty quickly. But watch. Go ahead and write this down. 3x to the 4th. If we were to write down the process for taking this guy's derivative, right? When we took the derivative, what did I say to do with that exponent? Yes, multiply. So I'm going to have you write this because I want you to see how this process works. Multiply by the exponent, the power, if you want to do that. Once you brought the 4, notice you ignored the 3, right? You just, let's say, we're going to still ignore those constants out front. But if I were to say, if you were teaching somebody in pre-calc how to take a derivative, you'd say, well, you multiply by the exponent and then do what with it? And then subtract, right? And subtract 1 from the exponent. To integrate or to find an antiderivative, you do it in reverse and the opposite operation. So instead of subtracting 1 from the exponent, guess what we're going to do first? Add 1 to the exponent. That's what this is saying. Instead of multiplying by that exponent, guess what we're going to do? Divide by that exponent. So it's an inverse move. So watch. Just a really easy one, just so you can see it. If I were to say, what's the derivative of x squared? You'd say 2x. If I were to say, what's the antiderivative? You do the opposite. You add 1 to the exponent, and then divide by that exponent. That's easy, right? And guess what else is on here? Plus Carl. Now they're checkable too. It's kind of nice, right? Because they're equations, they're checkable. Like if I said x plus 2 equals 7, and Tyler says, oh, x is 3, I'd say, right? So if you tell me the antiderivative is x cubed thirds, its derivative better equal x squared, does it? Bring the 3 up front, cancel them, knock it down 1, right? And what's the derivative of Carl? All right? So the derivative of your answer needs to be, you're going in reverse. So we're going to practice that, and then we're done for today. Yep. Yes. Yes, for what's called an indefinite. Do you see how there's no limits today? Okay. That's called an indefinite. It's a process. It means when you see this symbol without the limits, it means find the antiderivative of 3x, or it's being asked the derivative of what is 3x. I would just put the 3 out front in your brain and on paper. It doesn't affect anything. So the 3 is just a constant. Then you're going to add 1 to the power, making it a 2, and divide by that power. And then you're not going to forget my good friend Carl, the constant. You just anti-differentiated it. All right? So, how could I check it again? If I wanted to. This was a quiz question. You're like, oh, I want to see if mine's right. What would you do? Bring the 2 out front, become a 6, over 2 is 3. X to the knock it down 1. You see how they work in reverse? Again, it's the same as if I said, hey, how would you check this one? And you said, well, I'd square the 5 to make sure it equals to 25. It goes in reverse. So let's go do this one. You need to see the power in order to work with it, just like with our derivative. So we're going to write that as a single term to a single power. Did you hear me say a single term? In expo algebra, they probably called that a monomial. But single term. This is not a single term. Okay? So now that I have it as a single term to a single power, I will add 1 to the power. Be careful, because there's arithmetic. There's negatives, and there's fractions, and there's negative fractions. Alright? So what do I get when I add 1 to negative 3? Negative 2. Then I divide by that power. And then I add Carl. Right? And then just like when we did derivatives, we never leave negative exponents. So it's going to go in the denominator plus c. You just anti-differentiate it or integrate it. It's the same language. Okay? Basically, you go in reverse. So let's go to letter C. If I were to write that as a power, what would I write it as? X to there. I need it as a single term to a single power. Now I'm going to add 1 to it. Disguised as 2 over 2, right? So I'm going to say, well, that's x to the 2/3 divided by 2/3. But we don't want to divide by 2/3. So guess what I'm going to do instead? Multiply. Yeah, you're thinking ahead of me already. Multiply by what? The reciprocal. What's wrong with mine? Because it's going to be awkward at first. Right. Carl needs to be there. You'll be missing an infinite amount of solutions to our word problems if you forget Carl. So maybe this is just a process today. And again, how could you check it? Do the derivative. Bring the 2/3 out front. 6 over 6, it's gone. There's nothing in front of here. Knock it down. 1. Whoops. It's x to the 3/2. Wait. Yes. Sorry. X to the 3/2 because I add 1 to the power. See, mine didn't check. I didn't even do that on purpose. I could say I did it on purpose to show you how you can find your mistakes, but I didn't. That was just a brain fart. Now, letter D. There is no product rule. There never will be. We're going to deal with products differently, but one of the ways we're going to deal with them is to distribute, so we can get those single terms. I keep saying single terms. All right? So we're going to multiply those, but we have to remember exponential algebra. What is x to the cubed root of x, I'll leave it like that, times x? You need to be pretty about that fast at doing it, or you're going to get crabby with yourself. So say it again. X to the, yeah, because it's 1/3 and x to the first, which is 3/3. We add, so it'd be x to the 4/3 when I distribute that in, minus 4x to the 1/3. That's the first thing I do is get those single terms. Is there a rule for subtraction? Yeah, it says you can do them separately. I would write them down separately. I mean, it's just a pain. But I would grab that 4/3 and add 1 to it. What would you get? What would you get? 7/3, and yep, 7/3 divided by 7/3. So what am I going to write? 3/7. Okay? This is the antiderivative of x to the 4/3. Minus, constant stays put. How are we doing? It's a process today. And then I'm going to add 1 to this power, disguised as denominator over denominator. It's awkward because you're used to bringing it out front, knocking it down 1. Now you're building it up and sending it, dividing by it. So this would be x to the 4/3. Can you guys anticipate why I left some space there since I do integration all the time in Calc 2? Why did I left it for multiplying by the reciprocal. You'll kind of get used to how to organize. All right. What's one thing wrong with mine? The plus c, and it matters. You're going to get crabby with yourself when you see -1 because you forgot Carl. Or if you forget to enter it on Delta, it gives you red X. It happens. All right, what else should I probably do? Cancel the 4s. How are we doing? Okay. Look at the next one. Did I give you a rule for division or a quotient rule? And it's not because there's one coming, it's because there isn't one. All right? We have to deal with quotients all differently. It just depends. This is the kind now that BC kids would get wrong the most. because they've learned about 5 other ways to deal with quotients that are more complicated. So they always look at this and they go, nothing's working. And I say to them, if it makes a heart, you can break it apart. And they'll be like, oh, and I forgot the easiest way to deal with them. Only if it's kind of like over a single term like that. You can't do it if it's like this. To be honest, I don't know that I know how to do this one. Just flipping the fraction, I don't even think it has an antediluvian. Because I'm going through my, if it is, it's beyond Calc 2. Because none of those techniques are popping into my head. But this one, we're just going to break it apart. We're going to make it x over root x plus 1 over root x dx. That's my first step. What do you think step number 2 is? What do you think I'd do next? Yeah, I would actually consider 2 separate antiderivatives. And this one, might, if I don't know it, I might go so I can see these. Right? I want to see all these powers. How's that so far? There's a lot of fractions and a lot of exponential algebra. So what is x over root x really? I haven't integrated anything yet. I'm using exponential algebra. What's x over the square root of x? Root x. Yeah, it's just x to the 1/2. You subtract those fractions, and then boom. Now it's ready to integrate, also known as anti-differentiate. So here's my directive to you. Anti-differentiate x to the 1/2. It means find its antiderivative, also known as integrating. It's all the same language.